So a derivative of a function, y equals f of x, is denoted in two ways, and we need to be able to talk about them correctly. So the way that we pronounce these two things, which are both very acceptable ways to talk about a derivative, is the following. This first one, you would pronounce f prime of x. So the little tick mark up there, the little f with the little dot right there, that's a tick mark. It's like a quotation mark. It's prime. That's how we determine that we are finding the derivative. It is f prime. The second one, dy over dx, is actually the derivative, that's what the d stands for, the derivative of y with respect to x. That would be technically how you say all that. We're going to call it dy over dx, but it is the derivative of y with respect to x. It's telling you what equation to find the derivative of, y, in regards to what input value, x. Because when you get into super advanced calculus, it's called multivariable calculus. You have to determine which of the multiple variables you're finding the derivative of, but you do not have to worry about that until college. But the derivative itself, this f prime of x, or derivative of y with respect to x, is a slope generator equation. It's going to give you an equation that provides you with slopes at different points along your graph. So again, kind of what we did on this warm-up today is we started with the slope of like a secant line, so something that looked like this. Secant means that it's touching the graph in two places. Let me draw a better straight line. So that's our secant line. That's our average rate of change, which we had been finding since then. But it required 2 points. What we want to be able to do is not figure out what's happening between 2 points, but what is happening at a tangent line of just 1 point. The problem is, if we use what we know beforehand, and we kind of talked about this before, we have no idea how this line is actually tangent to that 1 point. There's all of these options for how it could be tangent to the line. So we needed calculus to determine what that slope at a particular point is, which is your derivative, so that we can actually figure out which one of these lines is correct. So we have a definition of a derivative, because when we were doing that on the graph on the Desmos slides, what was happening and what the computer was doing is it was actually running a limit for you. We have a definition here of a derivative, and it is a limit statement, which means we have to utilize the things we've learned about limits. But the definition of a derivative is f prime is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Here's something that you should initially think about when you're thinking about this limit. When we did limits analytically, we took the limit number and we plugged it in. What happens if I were to plug in a 0 right here, right now? Can there be a 0 in a denominator? No, so that's a problem. So when we use the definition of a derivative, you will have to do some algebra before you take the limit, and then you do the calculus. The hardest part is calculus is not calculus. The hardest part is going to be algebra. Okay? There is a second definition of a derivative when we get more specific and we actually want to find the derivative at a certain point. So let's say we're not interested in finding an equation this time. We actually want to know at a specific point, like we did on the Desmos slide, what exactly is the slope at a particular point. Basically, this is the instantaneous rate of change formula for a particular point. This limit statement is f prime of a is equal to the limit as x approaches a of f of x minus f of a over x minus a. And again, if we were to plug an a in for x right now, right here, what would happen in the denominator? You'd have a minus what? A, which is what? Ooh, now we've got a 0 in the denominator again. So when we use this limit statement, it's going to require us to do some algebra before we can do the calculus and take the limit. Okay, but you have made it this far in your math career through all of the algebra classes, so you know the algebra that goes into it. In these two examples here, we're going to use these two definitions of a derivative to differentiate f prime of x and f prime of 2 for these two functions. Okay, use your nice, neat handwriting on this. For the first one, if we want to find f prime of x, that's the first definition. It'll give us an equation, not a number. We're going to find the limit as h approaches 0 for f of x plus h, which means we're plugging in x plus h to the equation, minus f of x, which is just the regular equation, so x squared. Does everyone see how I plugged in x plus h into the original equation for the first part? All of that is over h. If I were to plug 0 in right now for this limit, I would be dividing by 0. I already know I can't do that, so I'm going to have to do some math to make sure that that h cancels out and goes away. Here's the math we're going to do. Now, it's going to seem repetitive to continue to write that limit statement, but you have to write the limit statement until you actually take the limit. So don't lose that. That's important. But what we're going to do is we're going to actually multiply out this x plus h squared. That's the perfect square factor. If you don't know how to multiply that out quickly, you would have to FOIL it. But this does have a pattern that it's the first thing squared plus 2 times the combo of the two things plus the second thing squared. And again, if you don't know that pattern, then just FOIL that. X plus h times x plus h. You would get what I just got. Looks like I've made it worse, but in fact, what do you notice can happen in that numerator now?
X squared can cancel out.
X squared can cancel out. Okay, so we rewrite just because we need to see some things. So we're taking the limit as h approaches 0 of the things that are left, which is 2xh plus h squared over h. Can I plug 0 in yet? No, because it would still be in the denominator, right? And it would make it undefined or probably a whole. So we know we can't do that yet. But hopefully your spidey senses are tingling because what is the same in both terms of the top? H. Let's factor it out. We would have the limit as h approaches 0 of h times 2x plus h. I just took out one of the h's. And then, oh my goodness, do your spidey senses see what's going to happen next? What's going to happen? What cancels? That's what I needed. I needed the h in the denominator to go away so that I can have a limit statement that won't break. Now I have the limit statement, the limit as h approaches 0 of 2x plus h. Let's plug in 0. But we're plugging it in for what letter? X or for h? H. So this is going to be 2x plus 0. Well, what's 2x plus 0, y'all? 2x. The derivative of x squared is 2x. That's the formula that gives me the slope for the line tangent to x squared at any point. Yes, so at the beginning, what I'll show my work here. Just, I know the bell's about to ring, but I'm going to finish this real fast. When I did x plus h squared, in my head, I did foiling. This is x squared plus x times h plus x times h plus h squared. And then there's 2x plus h's. So I combine them together. But that is a pattern that I just knew. Okay, so before lunch, we had done the definition of a derivative for x squared. So if we look back through this just to remind ourselves what happened, the definition says for us to use f of x plus h first, which means plug in x plus h to the equation. So I did that. And then minus f of x, which is just the function itself. So that first step right there, what I did was multiplied x plus h times x plus h, which is just some algebra over here. I used a shortcut because I knew the pattern. We noticed that x squareds can cancel out. We noticed then that there is a GCF of h. And then finally, the h's will cancel out. Once you can plug in 0 so that it doesn't become undefined or 0 over 0, you do, and you get an equation answer. But that second definition of a derivative, the definition of a derivative at a point, is going to allow us not just to find the equation for the slopes, but to find the actual value of the slope at point 2. So if we follow that equation, which I'm not going to be able to show you at the same time, it's too far away, but it's the second box, the second thing we highlighted. It says f prime of a, or f prime of 2, is going to be equal to the limit as x approaches 2 for the function f of x, which is x squared, minus f of a, which means plug in a, or plug in 2, over x minus a, which in this case is the number 2. If right now I were to plug in the number 2, I'd have 2 minus 2 in the bottom, which would mean the denominator is 0. So that's a problem, and we need to get this to cancel out. Does anyone notice what special pattern is in the numerator, though, right now? Say again? We're subtracting two things that are perfect squares. So what can that immediately factor to? It can factor to x minus 2 times x plus 2. That's just the difference of two squares. Normally it's written x squared minus 4. You might have recognized it better that way, but 4 is just 2 squared. Okay, what are your spidey senses saying right now? Cancel out x minus 2 over x minus 2, correct? So I'm left with the limit as x approaches 2 for x plus 2. Can I plug in 2 now and get a number that's not 0 over 0? Great. If we plug that in, that's 2 plus 2, which is 4. The slope of the line tangent to x squared at the point 2 has a slope of 4. So we have found the slope of the line tangent to it. Okay. So far we have used the definition of a derivative and the definition of a derivative at a point. The first one is going to give you an equation. The second one is going to give you a slope because you're plugging in a point essentially. Here's what's cool though, a little bit extra. If we took this equation and we said, well, what's happening at the point 2 in this slope equation? What's 2 times 2? So we've done the same thing. The derivative formula gives me a formula to use for any value of x. The value of x I care about, right, for this problem is the value 2. So either way, you can find the slope of the line tangent at that point. Can we do it again? This one's a little bit simpler. Okay, then we're going to do the same thing for the equation f of x equal to negative 5x plus 4. The first thing we're going to find is the equation of the line tangent to it. Then we'll find the actual slope at a particular point. So to do this, we're going to take the limit as h approaches 0 of the function. First, plug in x plus h. So we have minus 5 times x plus h plus 4 minus the regular equation written down again, negative 5x plus 4, all over h. So again, this first part right here is just the regular equation, except that I'm plugging into x, the expression x plus h. Let's do some algebra. The algebra I see is I'm going to have to distribute this, and I'm going to have to distribute this. Cool. So we have the limit as h approaches 0. I have to keep writing that because I haven't taken the limit yet, of negative 5x minus 5h plus 4 plus 5x minus 4 all over h. Did we follow that distribution? Okay. Once we have all of that, are your spidey senses tingling? what can happen in that numerator?
You can cross out 5x and 4.
So the 5x and negative 5x cancel out, and then positive 4 and negative 4 cancel out. Good eye. Which means we would have the limit as h approaches 0 of negative 5h over h. I still can't technically plug in 0 because I would get 0 over 0, but what do you notice? We have an h on top and bottom, and it's just a single term, so we can get rid of them. So really, this is like saying take the limit as h approaches 0 of negative 5. Are there any h's left at all? No, so if we plug in 0 for h, what number do we get out? We still get negative 5 out. Ooh, weird. I told you earlier that the blue equation, the definition of a derivative, should give us a formula. I know that this is a number, but it is technically still a formula. It's a constant. The slope at any point along this line is going to be negative 5, which makes sense. Isn't this a linear equation? Linear equations, well, this one goes down the whole time. Every single place that it goes, what slope does it have? Negative 5. This is y equals mx plus b. The slope is negative 5 everywhere. We've just proved this using calculus. Just again, to practice using the definition of a derivative at a point, we'll do the second part. We're going to do f prime of 2 equal to the limit as x approaches 2 for the equation. Write the regular equation, negative 5x plus 4, and subtract the equation with the number plugged in, which would be negative 5 times negative 2 plus 4. Oh, not negative 2. Why did I do that? Okay, all over x minus 2. We start with this distribution and a little bit of cleaning up some algebra or some computations. We have the limit as x approaches 2 for negative 5x plus 4 plus 10 minus 4 over x minus 2. What cancels out here? The 4's cancel. So I have the limit as x approaches 2 of negative 5x plus 10 over x minus 2.
I think you wrote negative 5x minus 4.
Where?
Is it supposed to be plus?
Oh, it's showing supposed to be plus. Thank you. That way it actually cancels. Thank you. So right now, if I were to plug in 2 to do the limit, because when you're doing limits analytically, you just plug the number in, the denominator would still be 0. Problem. So we have to figure out a way to continue to factor and simplify. I notice that the top two numbers are both divisible by negative 5. And if I divide both the top terms by negative 5, I have 1 and negative 2 left. Then x minus 2 is going to cancel. So kind of like the ending of the blue part, if I take the limit as x approaches 2 of the number negative 5, are there any x's left for me to actually plug 2 into? No. So if I plug it in, air quotes, because you are still technically plugging it in, you just don't actually have to plug anything anywhere, you get negative 5. Which just shows you that at any point along this linear equation, the slope is negative 5. You've known that about linear equations since Algebra 1. That y equals mx plus b, m is the slope everywhere. So the definition of a derivative, yes, is a bunch of algebra to work with, but it's all algebra you know how to do. The first few problems on your homework, if you look at your homework for today, the first, I think it's 6 problems, need you to use the definition of the derivative to find the equation of the derivative. That's the blue equation. So when you're doing the first 6, I should see algebra like that on your paper. Because the definition of the derivative is the reason we're going to be able to do the things that we do on the next page. So make sure that when you practice that one, you're practicing, bless you, the entire definition of a derivative. Yes, leave yourself lots of paper. Okay, so here's the deal though. That's a lot of work to find derivatives. So mathematicians worked on this, and they're like, there's gotta be some shortcuts. There are some shortcuts. On the back page here, we're gonna start learning derivative rules, and it's gonna take us through the end of the year to get through all of the rules that we're gonna go over, and we're not even gonna go over all of them. But it's gonna allow us to do derivatives for more complicated functions without having to plug in x plus h or x minus a. The first derivative rule is called the derivative of a constant rule. Please don't overthink it. It's just saying that the derivative of any plain number with no letter attached to it is 0. Great? Can we accept that one? Fabulous. The next one is called the power rule. The power rule is super commonly used. It's used when you have x to some power, like a squared or a cubed. What you do for this rule is you will take that power and you're going to multiply it in front of the function. That's how we get this number here, n. And then simply, you're going to subtract 1 from the exponent. We'll see examples of this in a second. The next exponent rule is called the constant multiple rule, meaning if you have a constant number in front of a function, you can basically just do the derivative if you take that constant out and put it in front of the derivative. Kind of looks like the power rule, but I promise you it's different in use. Then you can actually take the derivative of the function itself. So any GCF that's a plain number, you can just factor out and keep in the front of your problem. The fourth and additionally most important, I think the most important are the power rule and then the sum and difference rule. The sum and difference rule is basically saying that if you have two terms added or subtracted, not multiplied and divided, that's different, but added and subtracted, and you're doing the derivative of the sum or the difference, then all you have to do is do the derivative of the first part and then do the derivative of the second part. You don't have to do anything when it's separated by pluses and minus signs. Each individual term gets to be derived separately, is essentially what that's saying. Okay. And then I just put a quick reminder on here. It's an algebra concept that a lot of students forget about. We definitely forgot about it based on what questions I heard during the gallery walk last class. If you have an exponent that is negative, you just take that term and put it in the denominator, which also means the backwards exists. If you have a letter in the denominator, to get it out of the denominator, you move it to the numerator, make its exponent negative. That's it. Another something you probably haven't gone over since Algebra 2 is that if you have a radical, you can rewrite it as a fraction exponent if you take the index and make that the denominator, and you take whatever power is right here and you make it the numerator. And we're going to practice this stuff. If you're like, what? There are notes I know from your Algebra 2 teacher somewhere in your old stuff you can find. Otherwise, I also teach Algebra 2 and have a whole lesson over doing both of those things on my YouTube channel. I digress. Okay. So we're finding the derivatives, but we're not going to use the definition of a derivative. We're going to use the rules, the derivative rules. When we are finding f prime of x for letter A, what kind of function is that? 7. Is it linear, quadratic, constant, cubic? What are we working with here? We see a x? No, which means it's a constant. What's the derivative of any constant? 0. Anytime there's a plain number, the derivative is 0. What that's saying is, for any flat line on a graph, the slope is 0. Is that true? A flat line on a graph has a slope of 0. Yes. Okay? That's the constant rule. If we're using the power rule, which we just did this one with the whole definition on the front page, but if we use the rule, what we would do is we take the power and we're going to multiply it in front, so it's going to be 2x, and then we're just going to subtract 1 from the exponent. What's 2 minus 1? 1. So g prime of x is 2x. That's exactly what we found on the front page when we did the whole definition, is that the derivative of x squared is 2x. You multiply the exponent in front and then subtract 1. So let's practice that again. What if it's negative 3x to the 5th? If I want to take the derivative, h prime of x, all I do is take this number and multiply it in front. There's already a number in front, so we just multiply it by that number. What's negative 3 times 5? Then you just subtract 1 from the exponent. So this is going to be negative 15x to what power? That's the derivative of negative 3x to the 5th. Now remember, we are finding the equations that generate the slopes, so you should be getting an equation every time that allows you to find more slopes. You're not finding the slope, you're finding the equation of the slope generator. Okay, those were your training wheels examples. Here's what the questions will really kind of look like. We're going to have y equal to x to the 4th minus 6x cubed plus 18x squared minus 72x plus 108. But every single term you do independently. That's what that sum and difference rule is telling me. So I just do it bit by bit. For dy over dx, which I changed how I'm writing the derivative because it's not f of x, it's y. So I changed to using this notation. Please note that. We're going to do just the x to the 4th. What rule should I use to derive just this part, x to the 4th? What's that rule called? Power rule. So just focusing on this part, I'm going to take the 4, I'm going to multiply it in front, and then I'm going to subtract 1. So what would the derivative of just x to the 4th be? 4x cubed. 4 minus 1 is 3. Part of it done. We go to the next part. We do the power rule again because you have another power. Negative 18x squared. Very good. I keep going. I go to the next term. I got a power again. What is the derivative of that little term? 36x to the 1, or 36x. And technically, this is still the power rule, but it will get easy. What's the power here when it's blank? 1. What is 1 times negative 72? And then what is 1 minus 1? 0. So this would be 1 minus 1, which means x to the 0 power. Well, x to the 0 power is 1. So this is just negative 72. And then what's the derivative of any constant number? Just plain number, no letter. So it goes away. This is the derivative of y with respect to x for the function we're given in part D. We just did the power rule like 4 times to get all of the sum and differences. So each individual term you can do separately. Separated by plus or minus is easy. Can I have you try one? You've got e. Yes, I know there's a fraction. Don't worry. It's a cube fraction. Here we go. You got it. So for this one, we're finding h prime of t. Notice I went back to the other notation because it was given to me in function notation. So when it just says y equals, that's when you use dy over dx. If it gives you function notation, that's when you use the prime. H prime of x. Cool. We should have had, because of this power, 18x squared. And then because of this power, positive 3x, and then technically because of this power, minus 12. Both of these things are constant. Pi is just a number, so pi squared is still just a number, so that goes away. Negative 5 is just a number. The derivative of any plain number is 0. It should just be 18x squared plus 3x minus 12. How'd we do? Okay. If we go on to the next one, we'll do this one together, and then I'll have you practice one that's similar to it. This one's going to use a little bit more algebra before we get started. When we're taking derivatives, we really like to see the powers because that power rule is so easy to use. So I don't like in this problem that I have an x in the denominator, and I don't like that I have a radical sign showing. I'd rather have all of the powers showing. So before we really do anything to take the derivative, I'm going to rewrite y, not dy dx, so that I have all of the powers showing. So I'm going to write everything in exponent form. The first term does not change. The second term becomes negative 2x to the negative 1. The x was in the denominator, and if I want it out, I just have to make its power negative. Its power was an invisible 1, so I make the power negative 1. Now it's in top. The second part, or the third part, sorry, is going to be 2 times x to the 1/2 power. 1/2 because square root can be rewritten as an exponent 1 over 2. The 1 comes from the back, the 2 comes from the square root, square root. And then the 10 is still chilling by itself. Okay, now that it is in exponent form, I get to use the power rule. So now I switch my notation. I actually take the derivative dy over dx, and I use the power rule. I have all of these powers to multiply by, and then a constant. So the derivative would be 15x squared plus 2 times x to the minus 2. Whoa, where'd the minus 2 come from? I thought we were supposed to be subtracting numbers. Shouldn't it go away? It's 1. Here, we're subtracting from a negative number. It's going to get more negative. So negative 1 minus 1 is negative 2. Okay, so then I keep multiplying. 1/2 times 2 is just 1. And then I'm going to do 1/2 minus 1. 1/2 minus 1 is negative 1/2. And if you're like, what? Here's what I did. I did 2 times 1/2 is 1. And then 1/2 minus 1, or 2 over 2, is negative 1/2. That's where I'm getting those numbers from. Now that's technically done, but if I were to stop here, it would be like asking somebody, how many miles do you live from the school? And they say 7 kilometers. And you're like, I didn't ask you kilometers, bless you. I asked you miles. They gave you this question with letters in the denominator and radicals. You give them the answer with letters in the denominator and radicals. So the correct way to finish this problem would actually be 15x squared, that one didn't change, plus 2 over x squared, put it back in the denominator, plus, I got a negative exponent, so it goes to the denominator, and then I make it back into the square root, because it's still 1/2. Again, if all of the things, if you can go from here to here, the y to dy dx, that's the calculus. To go from y to y and then the dy to dx over dx to the final one I boxed, that's algebra. So the hardest part of calculus is not calculus, it's going to be the algebra, getting all the notation correct.
So in those, are you allowed to have a radical number in the decimal?
You are. So that's mathematicians argue whether it's correct or not. If you had a math textbook or a professor that didn't let you have radicals in the denominator, you would just change this last thing to square root of x over x. That's the same. The textbook that we use actually leaves the radicals in the denominator, so I'm going to leave it like that. I don't love it. I would rather it be in the numerator, but that's just a personal choice. It's a good question. Can I have you try one? It's okay if you messed up. That's all I'm going to say. But I want you to try letter G. First, change everything to where it has exponents showing, then take the derivative, then try to put it back. I'll give you some time to think. So to get you started, if the algebra is what's messing you up, f of x is the same. It's rewritten with exponents showing as x to the 5th minus 3x to the negative 2. Pull it up. Plus 2 times x to the 1/3, 1 behind, 3 in front, plus 1/2 times x to the negative 2/3 plus 7. Negative because it was in the denominator, 2/3 because of the radical. 2 behind, 3 in front, 2/3. I'll pause again and let you keep going in case that's where we got stuck. Now do the calculus. Take the derivative using the sum and difference formula and the power rule. I'm going to go ahead and start writing on the board, but don't look up until you have your answer and see how you did. Okay, you can look and let's talk about where maybe we went wrong. Cleaning it up is hard because it's utilizing some algebra we haven't done yet. Yes?
How did you get 2/6?
2/3 times a half. Fraction rule says do top times top, bottom times bottom. So 1 times 2 is 2, 2 times 3 is 6. And then yes, I reduced it to 1/3 after that. So if you used a calculator to do that, it is 1/3. I reduced it in the second step because I honestly didn't see it when I did it the first time.
Can you still put 1/3?
Oh, 100% yes. 1/3 and 2/6 are the same. I just did it in my head and I didn't reduce my fraction right away. But yes, 1/3 would have been fine in that intermediate step. Okay, questions before we move on? I know when it's the radical, you're having to deal with fractions, and adding and subtracting fractions in our head has not been a strong suit this year, but we can get better. Also, you have a calculator. The last two problems look like they're going to be pretty complicated, and you could actually make this very, very complicated because we haven't learned the rules, nor will we learn the rules for what's called a quotient derivative for like a couple weeks. A quotient derivative is the derivative of a function that's a rational function, meaning there's something on top and something on bottom that's both a polynomial and a polynomial probably. And the quotient rule is not all that simple, which is why we don't learn it yet. So I don't want to use a quotient rule. So instead, I'm going to see if I can simplify this down to utilize it as a sum and difference formula. Meaning, I'm going to take g of x, and before I take the derivative, notice I didn't put the tick mark, I'm not doing the derivative, I'm just going to split this fraction by its denominator, basically undoing the fact that all three of these terms have a common denominator of 3x. And I can split it like this. If you think about when we did our trig proofs, we were able to split fractions when there was plus or minuses in the top, but not the bottom. So that's what I'm doing here. I'm splitting all the tops and bottoms, undoing them having a common denominator. When I do that, can each individual term reduce down? 8/3 doesn't reduce, but that's just a fraction. What's x cubed divided by x? Squared. Okay, that's cuter, much nicer. 5/3 doesn't reduce down again, but what is x squared divided by x? And then 4/3 doesn't reduce down, but what's x over x? 1 disappears. That is much better to be able to take the derivative of. That's only going to require us to use the power rule and the sum and difference rule when we split it at the pluses and the minuses. So now we do calculus. G prime of x is equal to power rule. This is 16/3 times x. 2 times 8, 16, still divided by 3. Plus power rule, this is 5/3. That's a constant, so it goes away. There's the derivative of that complicated g of x function. So until we teach you how to do the quotient rule, and honestly, if this works, don't use the quotient rule because it requires so much more work. This is how you would find the derivative for a big divide. So I want y'all to go ahead and try I. It's going to be very similar to that one we just did, where you want to split it by its denominator first and try to reduce it to potentially have an easier time doing the question. Like the first time, I'm going to start writing, but don't look up until you get stuck or are done. First is to split the fraction into bunches of terms. And we can do this because the plus or minus is in the top, not in the bottom. When we do that simplification, x to the fourth over x squared is just x squared. So you have 8x squared as your first term. You have negative 6x to the 1 as your second term. But then nothing really cancels out in the third term. And I don't want to leave it like that because that's an x squared in the denominator and that makes using the power rule hard. So I went ahead and I changed it to pi times x to the negative 2. Just switching it to the top, make the power negative. Now I have all these powers showing, I can use the power rule to take the derivative. dy over dx is 16x, that was the power rule, minus 6, that was the power rule, minus 2 pi x to the negative 3. I still have to subtract 1 from this, so it should get more negative. Which means I do have to clean it up at the end and put the negative back down in the bottom so that I give the answer the way they wrote the question. So it would be 16x minus 6 minus 2 pi over pi to the third power. Yes?
Why didn't you cross out negative 6 or minus 6?
Where? Here?
Yeah.
When I took the derivative?
Because it's a constant.
Ooh, it is not a constant unless it looked like this. Constants don't have letters next to them. This still had an x term next to it because x to the third minus x squared leaves you with 1x. So there's still a 1 right there. If it was straight up 0, x to the 0, then you would have been right and the 6 would have disappeared because it's a constant. But we still have this power of 1 to multiply by negative 6. Yeah, so if it had said 6, well, let me use an actual pen and not a highlighter. 6x cubed over x cubed and the whole x's canceled out, then yes. But we still had an x remaining, so we still had to use the power rule. That was a good question. Any other questions? So we're going to pause for today. This lesson is going to take us 2 days to do. The second part is about using this to do something. On your homework, which is not due next class because it utilizes all parts of the notes, you can do questions 1 through 18 for sure, but I think you could do 19 and 20 if you pushed yourself. So 1 through 20 you can already do. The rest of them I will teach you how to do next time. So I want to go ahead and stop here and give you some class time to get started because the first questions require you to use the definition of the derivative, which is what we did on the first page. And I know there's going to be questions on that. I think the power rule and stuff is really pretty simple, so once you get to 7, you'll be home free. But the ones at the top, I want to give you class time to work on. So we will finish these notes next class to talk about the slopes of tangent lines.